This is a talk I recently did at a conference. The title is The Importance of Practical Radioactivity in a Modern Science Curriculum. The aims of this talk is to explain why schools have radioactive materials and what activities that they do with them, the importance of their use, and to explore the multitude of issues surrounding their use in schools. So a bit of background, I previously, many years ago, have worked as a physics and science teacher. I was very keen on practical work. I saw practical work as a key to unlocking student engagement and love and passion for the subject. I, in 2013, joined CLEEPS, the School Science Advisory Service, and I worked there for about a decade, including working within the CLEEPS RPA service as a trainer, training school RPSs and RPOs, the people that go and visit schools to inspect their use. And in 2023 I became a freelancer, providing my own training courses and RPA cover for schools and colleges. So to begin, why do schools have radioactive materials? Well, it's in the curriculum. At GCSE and A-level physics, GCSE science and A-level physics, students learn about nuclear physics. It is a relatively short topic, but it's a very important topic. Students are naturally curious about this topic, and engaging with practical work is a surefire way to boost their passion for the subject. It is a required A-level practical activity, so students who sit A-level physics must handle radioactive materials themselves, which this forms part of the practical endorsement. So in terms of what they learn about within the curriculum, it's the properties of ionizing radiation. So they learn about alpha, beta and gamma radiation, X-rays, they learn activity, nuclear reactions, fission fusion. They learn what half-life is, and this is where they often do an experiment either with a protactinium generator, or more commonly the radon-220 gas mantle generator, to look at the half-life of radon-220. Both protactinium and radon-220 have a half-life of about a minute, making, you can get results within 5-6 minutes. They look at atomic structure, and then the more real-life aspects of radiation, so its use in medicine, in industry, etc. So schools can get away, if they just teach in GCSE, you can get away with the standard chalk and talk. This is what alpha does, this is what beta does, this is what gamma radiation does, copy it off the board. I personally feel that's selling the subject massively short. Again, this is an area students absolutely love. They have an interest in this, which is intrinsic, which is built into them from years of reading comics or playing games, films, Marvel, Spider-Man, or whatever it is, Incredible Hulk. They know what radiation is, but they have many misconceptions about radiation, and in the media, in the news, in general society, it's often given a bad press. So schools have these issues surrounding their use, which I'll discuss in this talk. And I just want you to think about your own schooling. Did you use radioactive materials in schools, in your schooling, when you were studying for your GCSEs or O-levels or whatever it was? I did a physics degree, I did physics A-level. I don't ever remember seeing the radioactive materials when I was in school, or college or university. So this is what schools typically hold. They'll have 3 to 6 of these seal sources. The one on the left is a kind of the I wouldn't say older, but it's a more traditional version, which is called a cup source. So inside that box resides a small metal source, typically americium, strontium, or cobalt 60. The more modern, or the more kind of like source which is gaining traction, is the one on the right, which is an aluminium rod, and the picture shows it in its housing, so you can remove the rod and then use a source to demonstrate the properties of alpha, beta and gamma. Many schools have small sets of rocks, so 4 rocks, just to show students that these are naturally occurring. Protactinium generators, so as mentioned before, these are to study half-life. Schools are very big on cloud chambers, so they love their cloud chambers. Traditionally, these use a small radium source, which I've talked about in a previous blog. Radium paint source, which is no longer suitable for use in schools because the radium flakes off the end. It's a small spot of radium paint. Some schools also have consumer items, so things like smoke alarms or glassware, so uranium glassware. Welding electrodes are the go-to cloud chamber source because they're very safe. Low dose, no chance of leakage of any kind. So that's what they should have, and schools which are doing well only have the standard school holding. But there, as you'll see in a minute, there's all sorts of sources out there. In terms of the actual practical activities, this is a really good list of activities that schools can do with the sources. So they can show the properties of alpha, beta and gamma. So typically they just show paper blocks alpha by use of a detector which is only sensitive to alpha. So no use using a Geiger-Müller tube here. The spark counter or ionization can's the way to go. So for beta and gamma, they'll do absorption experiments through either aluminium or lead. With gamma, they can study the inverse square law. It's quite a practical, quite a common experiment which is done. Another problem with school sources is they're quite old, and schools will typically have a cobalt 60 source, which is 15 or 20 years old, which has gone through a few half-lives. Meaning your gamma source is quite weak and it doesn't perform well in these experiments. So one tip for those of you with radium-226 sources is to use 5 mil of aluminium to block the alphas and betas, and your radium-226 does emit quite a lot of gamma. You can even do this experiment with an americium-241 source. You want a bit of paper to block the alphas, but americium-241 emits gamma, which will be picked up by the standard school GM tube from 20 or 30 centimeters away. So you've got a fair bit of distance to do the inverse square law with even an americium-241 source. A balloon experiment, which I intend to film and put on the website in the near future, just to capture radon decay products in the atmosphere to show students that, look, there is radiation all around us. Half-life I've discussed, cloud chambers I've discussed. Yeah, I mean, that's a good list there. You know, it really brings the subject to life. Why is it important? If we look at the progression of students from GCSE, where it's mandatory, to A-level, where you, as a student, you elect to study various A-level subjects, we see a reduction, and that we see a similar reduction from A-level to university. So as we go up the kind of education tiers, the proportion of students studying physics decreases. Only 1% of all students were studying physics in 2019, which is it's a sad state of affairs. The second point, almost half of students who quit physics at 16 in England say they did not enjoy the subject, with a quarter noting that teaching was poor. I find this statistic absolutely mind-blowing. How can you not enjoy a subject as brilliant as physics when we talk about the really, really, really small atoms, protons, neutrons, electrons, quarks, etc., to the extremely big, the cosmos, the Big Bang, the expansion of the universe, stars, black holes, and everything in between. That to me, that's what makes physics so interesting. It's for me, the two topics I really enjoy teaching and learning about is the nuclear and is space. So I mean, practical work again is a surefire way to boost student excitement, engagement about the subject. It also overcomes misconceptions, and radioactivity, unfortunately, does contain many student misconceptions. Many students think if you point a source at the absorber all of a sudden becomes radioactive. And that might be to do with the language activity activating. I've already talked about students love this topic, but then when we think about the future sector for the jobs which relate to nuclear radiation, there's so many jobs which are going to need trained physicists or environmental scientists or people with those skills in this area. So we got medicine, we got the use in medical diagnostics, X-ray, CT scans, PET scans, PET CT composite scans, radiotherapy to break down cancer cells. It's used in energy, and I wrote big and small. So we're talking about nuclear power stations, and in this country we are facing an energy crisis. More nuclear power stations should be built, in my opinion, to meet our ever increasing demand for energy and our over reliance on foreign imports. But also the very small, a big growth area is nuclear batteries. So I know China are doing a lot of work here, and that could lead to very small and safe batteries being used for decades to power various items in the home and elsewhere. It's used in industry, in non-destructive testing, so looking at faults within metal castings. It's used in security, keeping us safe, keeping us secure, at airports, at ports, scanning lorries, food safety, in education, in life sciences, and in space. Again, linking the very big to the very small. So if we ever want to go to Mars in the next few decades, we're going to need ways of protecting our astronauts from very high doses of radiation from cosmic rays. So issues currently with radiation protection in schools. So yeah, all this is great, but we there are issues which need to be rectified. And unfortunately, there are a lack of trained physics specialists in schools at the moment. So IOP, Institute of Physics research states that 2,500 new physics teachers are required each year. This number tends to be around 500. So there have been 25 years of chronic under-recruitment. So there's a massive shortfall. Teachers are often teaching outside of their specialism, and if there are a lack of specialists, there's less confidence, there's fewer practicals, and then we got a vicious circle. Fewer practicals, less engaged students. Less engaged students, fewer want to be studying this at a higher level. Fewer teachers being trained, and so on. So that cycle needs to be broken. So as a result, we have poor management of radioactive materials in schools. We have many schools with legacy sources, so materials that they should no longer have. And I've put the worst offender here. So unfortunately, some schools still have World War II dials taken from World War II fighter jets and submarines and the like. So these dials were painted absolutely laced with radium-226 paint. Radium-226 is very radioactive. It's mixed with a material called zinc sulfide, which when the zinc sulfide absorbs the energy, beta energy mostly from radium, it re-emits it as visible light, so radioluminescence. So the pilots were able to see their compass direction, their speed, their altitude with the radioluminescent dials. So after World War Two, I'd imagine that these these fighter jets would have been dismantled, parts sold off at auctions perhaps, and some of those people buying those parts might have been physics teachers back in the 40s and 50s, who would then bring the instrument into the school to show their students it's radioactive. I've often seen examples in schools where the glass plate at the front has been taken off to demonstrate, at the time, I can only imagine the teacher wanted to really demonstrate just how radioactive they were, and the glass would have blocks on those betas and all of the alphas. And again, this radium paint is really bad news. It's one of the worst offenders in schools because it flakes off, so you get the radium dust everywhere, and it's this nasty stuff. Some of you will already know about the radium girls. So these were the young girls who would be making and painting these dials rather in the 1910s and 1920s in America. And these girls had very high exposures. They would be licking their paintbrushes in between strokes to get the fine increments painted onto the dial, as a result ingesting large amounts of radium. Radium is also a bone-seeking isotope. It's a group 2 element, so if it gets into your body, it gets into your bones and into your teeth, causing all sorts of horrific injuries and problems, as you can see here. Other sources which schools shouldn't have would include powdered radon generators. So I described the use of a gas mantle generator earlier, but some schools still have the powdered version. So you've got 30 grams of a thorium compound in here, and thorium-232 eventually decays into radon-220. So the bottle's full of radon-220, and that was historically puffed into a ionization chamber, and the ionization current would decrease over time. So you can measure the half-life of radon-220 within the chamber. Experiment's absolutely fine, makes sense. The problem was the powder that spawns the radon-220. It's highly radiotoxic. After 30-40 years, the bottle disintegrates or starts to break down. So the fear of many RPAs that work with schools is that somebody moves this bottle and it gets engulfed with 30 grams of the thorium powder. Protactinium generators, shown on the right, you've got 8 molar hydrochloric acid, and there's a uranium salt dissolved within that acid. You've also got an organic solvent. The uranium within the uranyl nitrate decays into protactinium-234, which has a half-life of about a minute. So you shake the bottle and the organic solvent pulls away the protactinium, and you can get measurements of the half-life. It's not I find the results not to be great here. And these homemade versions especially are prone to leaking. So the acid would eat away at the seal, and then you just get this radioactive concentrated acid everywhere. So they can be quite nasty. So I've talked to you a little bit about the legacy sources found in schools, about the lack of an expert or somebody with experience. Other issues include the money, the financial. So the amount of time spent on this topic is small. It's a short topic, but again, it's one of the highlights of physics. It's something that teachers can use as a hook to reel their students in to study this at A level and beyond. So what I see, unfortunately, is some schools disposing of the sources. They just feel like they're too much hassle. They dispose of them. I have often seen such schools recruit a new head of physics or a new head of science who is wildly enthusiastic, who then wants to purchase sources again. So the school might have disposed the sources in January, got a new hire in the summer term, let's say in June or July, and then they would contact me wanting information about buying sources again, which is absolutely ridiculous because the ones that they disposed of would have worked as well. Another problem we have are lack of technicians within the school. So technicians are the backbone of the science department. They're the ones who ensure the practicals are working, offer advice on the practicals, work with the teachers to set up practicals which are successful. So if schools aren't recruiting technicians, if technicians when they retire aren't being replaced, there is going to be a massive gap in the school. This font of knowledge will no longer be there, and if they're not being replaced, it's going to cause the teacher to basically be flying solo and being more reliant on just using the textbook or getting the kids to copy out a diagram, and that's quite a depressing state of affairs. So I would suggest that if you want to help out in this area, we really have to champion the importance of technicians within schools. Another problem is there is a legal requirement. If you have radioactive materials, the employer needs to appoint an RPA, and also there needs to be training for teachers and technicians within the school. So I offer RPA cover to schools at a relatively competitive price. And within that is training as well. So any school that comes to me for RPA cover will get one free training place per year. And there's also the CLEEPS RPA service. So if you contact CLEEPS, they can help you find an RPA. So again, I was at a conference with radiation protection professionals delivering this talk. So this was aimed at them. How can we help as radiation protection professionals? So it's really helping schools with training in RPA cover at a fair cost, spreading the message to schools that this is an important subject. There's going to be a lot of jobs out there, a lot of expertise would be needed in now and in the future for radiation related fields. So increasing the uptake at A level and beyond. I've redacted some of the slides from this version of the presentation, but I did talk a lot about gender stereotypes and imbalances. Unfortunately, it's known that the uptake girls versus boys, that fewer girls compared to boys study physics at A level and beyond. So I explored some of my thoughts and my experiences with that. Working with organisations such as CLEEPS, who are champions for safe practical work in schools. The Institute of Physics and Ogden Trust, I know, also do a lot of work trying to get more specialists and non-specialists involved with physics and practical work. And this is just an example of some of the imbalance I discussed on the previous slide. We can see here that if we look at a subject such as history or even chemistry, it's pretty even. But then when we go towards the top, physics, girls compared to boys, it looks to me like a 25-75% split there. So it boils down to, and this is my experiences, and it's not, I mean, we have to look at the current research, but a lot of it would be down to a lack of role models. So, mostly physics is taught by men. So where there are female teachers, they tend to be more successful recruiting girls to do physics at A level and beyond. But also, when I did my teacher training PGCE qualification many years ago, my dissertation was on why don't girls study physics. And again, I don't know if it's true now as if it's seen as the most current research. But one of the reasons was the upbringing of the young girl from a very young age. We tend to buy our daughters dolls or things which need nurturing, and we tend to buy our sons, i.e., boys, things that they play with, practical things that require batteries or screwdrivers or whatever it is. So that was part of it back in 2007. That was part of the picture. And as a father of a 4-year-old girl, I am still taking that research to be the truth. So I am buying my daughter, children's versions of Bosch tool sets, remote control cars, small drones, and all sorts of toys that would be typically bought for boys and not girls, in the hope that she values the importance of being hands-on and having those practical skills which would hopefully help her in her schooling, science specifically, and anything else that requires practical skills. I hope that was of some use. Here are my contact details. If you are a school requiring any more information, you can contact me here. Again, I provide RPA cover for schools, training for teachers and technicians. You can visit my website for more information. Thank you.